Hey, the ability to process vast amounts of data has been a long-standing requirement of the supply chain industry. However, it can be very costly both in terms of time and processing power, particularly when you consider that optimizing a supply chain can take hundreds of incremental changes. Today on LokadTV, we're going to understand the sheer scale of data that is managed within a supply chain and also discuss how Lokad has developed Terabyte Scalability in order to deal with it. So Johannes, today we're going to be talking a bit about the research and development done at Lokad over the last year. So what have you been working on in 2018?
So 2018 has been the scalability year for us. I mean, we have been working almost continuously for a year in increasing the scalability, and compared to the same date last January, we have increased our processing capacity by basically a factor 20 or so, which put us well within the range of processing multi-terabytes data sets relatively at ease. I mean, there is no such thing as like easy terabyte processing considering the technology as it stands today, but it can still be made relatively straightforward.
Okay, factor of 20 sounds like an incredibly large improvement. So what sort of steps did you have to take to kind of reach this improvement?
So Lokad is a platform designed for quantitative supply chain and supply chain optimization, and the way technically it's accessible is that you can write scripts in our own homemade scripting language called Envision. And this language is designed not only to be very specifically addressing the needs of supply chain in terms of expressivity to solve the right kind of problems, it's also designed to be to facilitate large-scale processing. And until last year, Envision, I mean, a single account could for one of our clients could within Lokad could hold several terabytes of data, but a single script, so a single piece of code, would basically be at any point of time be executed on pretty much, it was not entirely true, pretty much a single machine. We had already implemented scale out, so the idea is that you can distribute over the calculation of many machines for specific components, such as the machine learning ones. But broadly speaking, when you were just sorting the data, let's say, it was happening on one machine. Large machine, yes, but one machine. And what we rolled out in 2018 is a completely upgraded architecture for the back-end execution logic of what is happening, behind the hood for when you execute an Envision script. And nowadays you have like automatic parallelization across not only multiple processors, multiple CPUs, but directly over actually a fleet of machines, which means that a single script that is performing, let's say, a simple operation such as sorting the data, by date, by product, by store, by date, by price, by whatever, it's the task at hand requires, now can happen over a fleet of dozens of machines, which means that it can happen literally way faster.
Okay, let's talk a little bit about Envision here. How does Envision, for working and in making these improvements and improving scalability, how does it working with Envision compare to working with other programming languages, like something like Python or something like that?
I mean, Envision is a domain-specific programming language. Python, Java, C#, C++ are a generic programming language. What you get out of a generic programming language is a capability to pretty much do anything. The price you have to pay for that is that there is classes of technicalities that surface into the programming environment. What do I mean by classes of technicalities? I mean that, for example, yes, you can do distributed computing with Python, no problem. It is possible, but it means that you need to very specifically write your code in a way that take advantage of very specific libraries and framework to have those calculations happen over a fleet of machines. And you will have to configure yourself probably a cluster of machines so that it can execute this distributed logic. And if you have several concurrent programs that execute over the same cluster, just because you have different scripts, different users, different needs, well, you will need to have all the plumbing in place to share the resources, the bandwidth, the disks, the CPUs, and whatnot. And all of that is precisely what Envision does in a way that is completely built in for you. So what you lose is that you lose a lot of expressiveness, which is okay because, again, Envision, the one reason it can survive, it's not broken despite having lost a lot of expressiveness, is that we are specialized on a specific type of problem, which is basically supply chain problem. So we don't try to solve every single problem. We don't try to write an engine to play chess or to do like a 3D modeling for virtual reality. No, it's very geared towards specific types of problems.
Okay. So what you're sort of saying is a lot more sort of simplistic to use Envision rather than sort of another sort of programming language.
Exactly. I mean, writing a script that process tables that are containing several billions of lines to perform, the sort of analytics that you would expect in a supply chain context, such as let's try to have an estimation of the cost and impact of stock rollouts across my large networks for the last 3 years. It's a sort of analytics that you could do with just literally a dozen of lines of code, but code that is like easy to write. When I say easy to write, I mean it's never that easy to write code, but that is no more difficult than, let's say, writing an advanced Excel sheets that does, fancy averages and fancy sorts and fancy lookups over the data.
Okay. And what were sort of some of the key insights and key kind of breakthroughs that sort of led to these improvements?
So one, just to understand where we were starting from. So 1 year ago, Lokad had already, I would say, many big data ingredients in place. One of them is to have a columnar approach on a columnar take on data storage. So long story short, traditional SQL databases adopts a tabular storage. It means that when you have a table, you are storing lines of data. And if you have a line of data, this line sits together. And that's your unit. So basically that makes a tabular database is very efficient at performing small updates of data, or read or writes, line per line. In contrast, over the last decades, whenever you want to do basically big data analysis, what has been being developed is a columnar approach. So basically, when you have a table, let's say you have a table with 20 columns, you are going to store data packed by column. So what does that mean? It means that when you perform an operation, such as, for example, I would like to have, I have the per unit price and I have the quantity. Let's say you have a table that represents, sales history. So you have the per unit price and you have the quantity. So that's 2 columns. Now you want to know the total amount of sales. So what do you need to do? You need to multiply the price by the quantity and do the sum of all of that across the table. Well, it turned out that your table might have 20 columns, but the operation that I just described is only touching 2 columns. So if you have a columnar storage, the main upside is that every operation that if your operation touch only a few columns, only those few columns will be processed. The rest can be just ignored. If you have a tabular format, well, the other columns are completely in the middle, and you can't really skip them.
But the drawback would be that if you're adding additional lines, if you're working kind of real time, if you're having a columnar approach, if you're adding a line, you'd have to work with every single column.
Exactly. So basically, when you are adding a line, one line, you have in the end to touch 20 columns. So you have 20 access to the data, which makes it relatively inefficient. So columnar storage, bottom line, is that's why it's typically sort of big data-ish database technology, which is suitable for batch analytics, not exactly real time, but more like, which is exactly the sort of analytics that you're interested in supply chain. I mean, it doesn't mean that it cannot be refreshed, every minute. It's just that it will not be refreshed every millisecond.
Okay, let's talk a little bit about some of the costs that are associated with processing power and the costs that are associated with working with these large amounts of data. By implementing now sort of terabyte scalability, how's that affected the costs of working with data?
Actually, quite a lot. I mean, the most expensive resources when you try to optimize a large-scale supply chain is the cost of what we call supply chain scientists. Maybe other companies would just refer to them as data scientists, but we prefer to have people that are kind of knowledgeable about the problems they're trying to solve. So supply chain scientist it is. But bottom line, those people are not free. It's a relatively scarce resource. It's a challenge to find people that has the right talent, and then it's expensive to train this person so that he or she can acquire all the necessary expertise as well. So bottom line, the scarce resource is not CPUs or disk or bandwidth. This can be cheaply bought from your favorite cloud computing platform. The scarce resource are the talented people you have to work on the problem. And now, what happens when you enter the realm of terabyte processing is that everything is slow. That the reality is that everything is slow. So you want to crunch a terabyte of data. Well, it's going to take quite a while. What do I mean by quite a while? Well, if you really have 1 terabyte of data to process and you're doing like a non-trivial, calculation, maybe something that involved, probabilistic calculations with random variables, analyzing, let's say, for example, lead times, where you want to sum tons of lead times so that you can figure out the total lead times across your network from a probabilistic fashion. So we have like a terabyte of data to process to generate probably something that is going to be an order of magnitude larger than your original data as soon as you inject all those probabilities on top of it. Well, it's going to take, I would say, from our old perspective, let's say 1 year ago, that was going to take literally hours. And now it's taking minutes. And what does that mean? It means for the supply chain scientist, who is the scarce resource, instead of having someone who is saying, okay, go, let's do an iteration, and then, well, the thing is just going to compute for the next 90 minutes or so. So I'm just going to grab a cup of coffee and start reading papers, because there is not really much better things to do for 1 hour and a half. Now the idea is that you can, if you have processing that happen much faster, you can stay focused on the task, get the results, and move on to the next thing, instead of just being stuck waiting for the result that will come out from the machine.
So if anything, it's bad news for our supply chain scientists, because it means they get to have sort of less coffee breaks.
Yeah, absolutely.
So what does this breakthrough kind of mean for the real world? I mean, now we're able to sort of work with much larger data sets. Obviously, that's the real benefit, and we're able to work with them a lot quicker. What about in the real world? Are there any other benefits that we're seeing?
Yes, I mean, one of the key danger, and when I mean danger, it's like root cause for failure for quantitative supply chain initiatives, is just the time it takes to get it right, get it working, get it completely polished, so that you don't have annoying edge cases that lingers, where 99% of the decisions generated, the supply chain decisions generated by your systems are good, but the 1% that remain is still pure crap, and so in the end you still need a tons of manpower to manually grind through all the edge cases that are not properly handled, and so which in the end kind of completely defeats the purpose of having like advanced machine learning automation to perform the optimization. So bottom line, the danger is that this process to eliminate all the edge cases, to really sharpen the decision making numerical recipe, this process can just take too long, and this is deadly, because at some point people lose faith in the fact that the initiative might even succeed. If you're very slow, then basically chances are that the IT is going to be disrupted in the middle. For example, if your project takes 2 years, well, chances are that you might have like one chance out of 3 that there is an ERP upgrade in the middle. So basically, you were starting to optimize a supply chain, and then there is like a massive change that happened within the IT of the company, and most of what you've done just falls apart just because all systems are kind of being changed. So again, and the longer you wait, the more things can just disturb. Also, the business itself can undergo dramatic transformation, which makes your earlier work kind of moot with respect of the new new business changes, etc., etc. So basically, in short, there is tons of driving force that put pressure on getting the thing, in production fast. And if you cannot succeed within a few months to get this out of the door, then basically chances are that your initiative will fail. And that's where this agility is absolutely required, is that it might sound a lot, a couple of months, but if whenever you touch your terabytes of data, it takes, hours to get a result, it means that you're basically touching, this data and tweaking whatever your numerical recipe is, something like twice a day, or even once a day, worst case. And that things starts to be very, very slow.
So what you're sort of touching upon there is a kind of the iterative approach that
Yes.
it takes to sort of optimize a supply chain. So why is there such an iterative approach? Why is it not a case of you can just press one button, you've got deep learning, it's going to be able to learn it, and you'll be able to get a good forecast and good results, and you can go from that? Why is there always this iterative approach?
Because reality has a way to get, in your way. It's very, supply chain is really about dealing with real world contingencies. There is so many like edge cases that just emerge from the very fabric of reality. What do I mean? I mean, you start computing an ideal, quantity to order, and you say, well, I've computed 80 units is exactly the best quantity to order. And then guess what? Well, pallets, it's either 0 units or 100 units, because it's packed over a pallet, and a pallet is 100 units. So 80 is not an option. So what do you do? Do you still order, but it's 100, or you don't? And things like that, you have dozens of them. You would think that, I'm going to consider that the value of my inventory gradually decay over time. But no, it doesn't. Why? Because there is a shelf life with a specific date on the end of every single box. So when you reach the shelf life limit, your inventory value drops from something to 0, or actually something negative, because now you have to pay to destroy this extra worthless stock. So there is, and the reality is that supply chains are complex. I mean, if we are talking of companies that operate over multiple markets, multiple countries, with many suppliers, potentially dozens of product lines and whatnot, there is tons of complications, and it's what we observed is that it's kind of wishful thinking to think that you can just sit down in a room and say brainstorm with the teams all the technical challenge that will emerge, down the line with the initiative. You cannot just say sit down with your supply chain team and say let's list all the small things that will derail the numerical recipe, that generates the optimized supply chain decisions. Reality has always its way to kind of surprise you, because you're going to discover, bizarre things, like there is one country that has a bizarre tax on something or whatever. And so, back to your initial question of the iterative approach, the only way to cope with this kind of endless stream of surprises is just to be extremely agile as fixing your numerical recipe when you actually face something that was unexpected.
Okay, so let's circle back to Terabyte Scalability and start sort of bringing things together. How does it change things for the outlook of Lokad, and what does it mean for kind of the future here?
We have made a tremendous, I would say, we have delivered tremendous improvement in terms of scalability processing. So that opens, I would say, tons of challenges that were just not accessible to us. It's not just about dealing with larger companies, because again, there is plenty of way to cheat your way out. For example, what do I mean by large-scale data processing? Let's consider a large retail networks. If your way to optimize, a large-scale retail network is to say, I'm going to take every single hypermarket and to process this hypermarket in isolation. Well, if I have, let's say, 200 hypermarkets, I only need like 200 machines, one machine dedicated per hypermarket, and it will scale. Yes, if you do it that way, it does scale, true, but it will not yield the supply chain improvement that you're seeking, because you're not doing any kind of network level optimization. You're just locally optimizing every single store in isolation, completely ignoring whatever is happening in the rest of the network.
So those 20 machines wouldn't be communicating with each other.
Exactly. If it's like silos, it's very easy to scale your processing if all you have is independent silos. And again, 1 year ago, we were already capable of doing that. The challenge is when you start thinking of, no, my network is just one network, everything is kind of connected. It is actually true, because you can actually ship inventory and materials and flow things across the network in pretty much any way you want. It's not, although there is plenty of ways that are just not profitable and doesn't make much sense, but it is possible. And some of those subtle ways might actually be very, very good ideas and very profitable ones. But the bottom line is that you need to have this system that can crunch everything like at once in relatively monolithic ways. So what does that mean for the future? It means that it opens tons of avenues for them to do, I would say, better kind of holistic optimization, where again, the curse of supply chain optimization is that you don't solve the problems, you just displace them. You have a look at a warehouse and say, oh, I'm going to optimize that, and no, what you've just moved the problem down the store or back to the supplier. So that's one avenue. Another avenue is now that we have significantly gained in scalability, we'll probably try to go back to expressiveness. So basically, to be able to express in ways that are more direct, more fluent, to have ways to reflect more fluently complex situations that happen in the real world in those Envision scripts, so that it's easier to deliver a numerical recipe that is really, really a good fit to address the real world situation.
Okay, great. We're going to have to wrap things up there, but thanks for your time today. So that's everything for this week. Thanks very much for watching, and we'll see you again next time. Bye for now.